I will begin with a word of prayer. It's a go time. So, dearly Father, we thank you for this day. I thank you for these students. Just ask you to bless this class. Help us to just understand a little bit more about your creation today and just to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so here's the attendance sheet. Remind me when I get my computer out at some point to show you some proof or something to top hat then, if you guys would. Otherwise, I will totally forget. So here, just like check past the blue line. All right, so we're talking about vectors, right? And just to summarize, what does a vector look like? We have something like A, and I'll be 3D here for a second. A1, I'll be 2D for a second. A1, A2, and we learned we could rewrite that as like A1 x hat plus A2 y hat. All right, that's essentially it. Now, in 2 dimensions at least, and I can draw a picture of this, right? And if I do so, I'll just draw it in the first quadrant because that's just kind of like easiest to picture. You can also write this as, what's another way we could write it? There's like a bunch of different ways, but here's another way. We could write it as the magnitude times the unit vector in the a direction, right? So, it's okay. So here, you guys are cracking me up. But I am easily amused, so there's that. So there's this one here, right? And that would be this piece right here. So this would be A1 x hat. And then there's the other piece, this guy right here, which we could look at like this. This would be A2 y hat. All right? Now, these two things are the x vector component and the y vector component of the vector. The vector component is, again, a vector. On the other hand, A1 and A2 are the scalar components. So A1 x hat is x vector component of the vector A, whereas A1 is just the x component. So when we just say x component, it's understood we're talking about a number. The word scalar also means number, right? We talked about scalar addition last time. That means multiplying a vector by a number. It's again the same use of the word, which has to do with like just the more geometric word scaling, right? Okay, so here's x, here's y. Now there's another thing we could do. You guys just got done studying, well, maybe not just, but at some point in your life you studied polar coordinates, right? In Calc 2, remember that? Unpleasantness. So we can bring that back again, and we can kind of use polar coordinates to describe the vector. Now before I do that, what was our definition of a hat? Remember? A hat?
A vector
Mm-hmm.
by A.
Right, so like, exactly. Take the a vector, multiply by 1 over a. Right? Now, and I can picture that, assuming that this vector is longer than length 1, right? The picture would look something like, oh, I don't know, here I'll draw it like this. Maybe this would be a hat. A hat is a vector of length 1 that points in the direction of a. All right? So in my picture, what's the magnitude of a in this case? About 3.4. All right? The magnitude of a here is about 3.4 by my guesstimates there. All right? So what's the other thing we could do here? We can describe a vector by a magnitude and a direction, right? And one way to talk about a direction is that it's a unit vector, right? Okay, so what's the other way you could talk about a direction for a vector in the plane? An angle, right? So we could talk about the standard angle, which would be, if I was to draw it in here like this, right? Measured counterclockwise from the positive x-axis. This is the so-called standard angle. And in view of the standard angle here and the discussion of polar coordinates that you had in your previous course, you can easily see that A1 should be equal to A cosine theta, and A2 should be equal to A sine theta, right? Because there's a right triangle here, and the horizontal side has length A1, the vertical one has length a2, and the hypotenuse has length a, which is the magnitude of the vector, right? So what does this mean? That means that you could also write this, right, as what? As like a cosine theta, a sine theta, okay? You could also write the vector like that. But what else can we do? We can factor out the magnitude, right? We can factor out the magnitude and we can write it like this. So what does that mean? What does that reveal to us? What's the relation between the unit vector and that vector I just wrote down, cosine theta, sine theta? They're equal. Now you're using a little theorem there, right? And the theorem, basically you're comparing this and that, right? And from that you're like, I have a thought, right? Which is that a hat is equal to cosine theta, sine theta, right? My apologies to anybody watching this later. The camera does not like that green. You guys can see it though, right? This is a pretty well written, pretty well lighted room as they go at Liberty. Like, this is probably one of the best rooms here. I didn't like it at the start, but I've grown to like this room. Its proximity to the coffee in the math department is very helpful. But so look, this is another way we can look at the unit vector. If you know, right, if you know the standard angle of the vector in the plane, you can find the unit vector simply by plunking down cosine and sine like that. So this is, but you notice that there's a big difference between, say, this, right, and that. Here we're just taking the Cartesian, dividing by the length. There we're using perhaps some trigonometry to find the angle, or perhaps it's given to you. All right, so you should keep these things in mind as you work problems in two-dimensional vectors, all right? Okay, so that's just a backdrop. What's the other thing we learned last time? We learned that the definition, if I have let's be n-dimensional here for a second. If I had an n-dimensional vector, da-da-da-dot, right? Like A with n components, yeah? Then, actually I don't think I even told you guys this last time, but for pretty much the same reason that I told you, the length of an n-dimensional vector would be, again, the sum of the squares. Now I think I did 3 dimensions. I actually drew you a picture for 3 dimensions last time, right? But you can pretty easily see that it's reasonable to define the vector length like that if we were in 4 or 5 or 6 dimensions. Why would we think about 4 or 5 or 6 dimensions? Do you have any idea? Besides just having some sort of wackadoodle theory of like hidden physics. And I'm not actually talking about necessarily physically spatial dimensions. I'm talking about like a mathematical space. So a good example of this would be, you have like a robot arm, right? If you think about a robot arm, how many parameters do you need to describe it? Let me draw a robot arm like this one. It's got a linkage here. It's got another arm, maybe it's got another linkage, right? So you've got this angle, theta 1, you've got this angle, theta 2, you've got this angle, theta 3, right? If this is a robot arm in a plane, right? What else do you need? You need like the angle that it's there, let's say. I hope I'm convincing you, like if you think about an arm and you start adding linkages, every linkage has an angle. Essentially every angle is a new dimension. If you wanted to describe mathematically that system, you'd need as many dimensions as you have angles, assuming the angles are independent. See, so is that something esoteric and like something that only belongs in the Big Bang Theory? I mean, definitely not, right? Like it's something you might find in a factory somewhere, right? So understanding higher dimensional spaces is something you need for real world problems. It's not just, you know, me talking to the math majors, although I am. Question, how does this formula simplify in 1 dimension, 2 dimensions, 3 dimensions? I think I talked to you about 1 and 2 dimensions 2 and 3 dimensions last time, but it's interesting to notice that this formula still makes sense in 1 dimension. Check it out. What's this look like in 1 dimension? kind of silly, but what is the square root of the square?
The absolute value.
It is. It is the absolute value. That's right. So in the case of one dimension, we just have that. And of course, in one dimension, what else do we do? It's very silly, but we just write this, right? So like in one dimension, we drop the vector and we just write that. And then there's all kinds of more annoying things to think about, which we have to face in physics, which is in physics, the magnitude is just like in a one-dimensional case is the absolute value of the thing, right? But we use plus or minus to indicate like up or down or left or right, something like that. One-dimensional physics is especially its own can of worms, yeah.
Could you write the magnitude of the vector A as simply A?
The magnitude of the vector A as simply A here?
Yeah.
See, here I couldn't. I mean, here, okay, so like this, I would say, what I'm trying to say is this is equal to plus or minus A. Because that's A in our notation. So anyway, what I'm trying to tell you is my drop the vector symbol, just use a letter notation. It becomes a little bit ambiguous in certain contexts, the way people write equations in one dimension. So just be aware this is really best suited for 2 or 3 dimensions. And different people mean different things in one dimension depending on who you're reading. So All right, enough about that. This is not a physics course. Let us not devolve into that. All right, so there's a quick overview of some of the things we did last time. And so next, we should talk about the dot product. Because the dot product is the key to understanding geometric problems, all right? And so I'm going to define it in n dimensions, and then we'll look at what its formula looks like in less. So if I have 2 n-dimensional vectors A and B, right? And so just to be clear, I mean like A1, A2, all the way out to AN, and dot product with B1, B2, all the way out to Bn, then the dot product is by definition equal to A1, B1 plus A2, B2 plus dot, 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 plus AN, Bn. Now writing that gets to be a drag pretty quickly, so we like to use that notation you learned in calculus 2, right? Except without all that annoying convergence, divergence stuff, right? This is just a finite sum. See, we could write this by the summation I equals 1 to n of A sub I, B sub I, right? So in 2 dimensions, you've just got the sum of 2 terms, right? In 3 dimensions, you have the sum of 3 terms. But it's very simple, right? You just multiply x with x, y with y, z with z, add them together. That's the dot product. So what is the dot product? Well, it's a number. First of all, it's a number, right? It's a scalar. It could be positive, it could be negative, it could be 0, all right? And what we'd like to understand today is, what does this do for us? What does it mean? All right? How can we use it to understand vectors more deeply? Okay, so, but before we get to all that, let's prove some properties of it. All right, so what's the first property that you might prove? If I use this notation, it's super easy. See, this is the sum I equals 1 to n of B sub I, A sub I, right? Why can I do that? Because AI and BI are just numbers, right? Do numbers commute? They do, right? But then what are we looking at? What is this? Well, this is exactly B dot A, right? So the dot product is commutative. Can you guys tell me some other properties before I get carried away here?
Well, it gets multiplied by a constant.
So when it gets multiplied by a constant, okay, so what would you say about that? Let me set you up here. So you're like C A dot B. You want to multiply the constant out there like that?
Yeah, and you can either take that in or out of the series.
That's right. So if we put it out here, we can multiply it in. We can just keep it with the A terms. And so we can look at it as CA, the vector CA dot B, right? Or we can look at it as A dot CB. These are three different things. Here's the scalar multiple of the dot product by C. This is the scalar multiple of the vector CA with B, dot product of CA with B. And here's the dot product of A with CB. And those things we can all see from the formula right there. Here's a more interesting one. If we have A plus B dotted with another vector C, how's that work? Right? So multiply the other thing inside. So what you're saying is do this. Like that. This is true. The dot product has what's called the distributive property. All right? And of course you can distribute on the other side just the same because it's commutative, right? If A dot B is B dot A, then we can also break up sums on the other side of the dot product. Do you guys want me to prove that? It's on the homework, so yeah. Well, I'll get you started. How about this? What's A plus B? What's the ith component of that by definition?
AI plus BI.
Uh-huh.
And then,
So if I have A plus B dot C, it's equal to what? The sum over I equals 1 to n of A plus B I times Ci, right? But then you can change this to that, right? Now these, what's the advantage of writing this is these are just the components, the scalar components I was talking about at the start of class, right? Those are numbers. Do numbers have a distributive property? They do, right? Real numbers. So this we can rewrite as sum I equals 1 to n of AICI plus BICI. Maybe put some parentheses here to emphasize they're both in the sum. And then the sum of a sum is the sum of the sums. Anyway, you can break it up into two sums and then recognize that you've got the dot product of B of A with C and B with C, and you're done. Right? If I write any more, I've solved the homework, but yeah. Now, did I ask you to prove this in 2 dimensions or 3 dimensions or n dimensions? Okay, so this is the kind of argument you want to give in n dimensions. Obviously, in 3 dimensions, you could just write out a mess of stuff and like collect it, right? But I would urge you to like think about using the summation type notation for these kinds of proofs because it will just simplify your life. And you can focus on the heart of the matter. The heart of the matter, the reason there's a distributive property is because you have a distributive property at the level of components. That is the heart of the matter, right? If you did this in the plus dot 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 notation, you'd have to do the distributive property once, twice, dot 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 dot, at least that many times. I mean, you have to do it over and over and over again, depending on how many terms you write out. But all right, enough, blah, blah, blah. Any other properties of the dot product we should talk about?
scalar.
It's a scalar, right? Let us emphasize that. The dot product is a number. Let's see here. How about this? What is A dot A equal to?
The magnitude of A squared?
The magnitude of A squared. Let's see here. So it's the sum I equals 1 to n of A sub I squared, right? A sub I. But you're right. That's the square root of the sum I equals 1 to n of like A sub I squared. Excuse me, that's not the square root. But if I take the square root of this, right? It's the square root of that. And this is what I just said is the magnitude of A a little bit earlier, hopefully. Okay, good. I had this like sinking feeling that I hadn't written this square root like 10 minutes ago, but all right, anyway, I did. So check it out. This is actually really important. So here's, I'll elevate it to a theorem. A theorem is really just a way in mathematics of saying, hey, look at this, it's important. So I mean, this rises to the level of a theorem, I'd say, although it's an easy one to prove, which is that the length of a vector is equal to the square root of the dot product of the vector with itself. Right? So in our notation, we can also say it's equal to A, right? So if I'm tasked with understanding something in terms of dot products, I think about this, all right? All right, so let's calculate some dot products. Oh, did everybody get the, oh, you haven't gotten over here, did you? No, 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 no. Ah. YouTube may be part of the group chat if we're not careful. I'm sorry, guys. I may have to start the video here. I didn't get to the group chat. All right. Well, just to be on the safe side, there's a video. There's a board. There's a board. Wait a minute. I want to start over.